Analysis of the common collector amplifier. So this is the schematic from before with our common collector amp, and we found the Q point was 6.5 volts and 89.2 milliamps. Now, even though the circuit is different, the method of analysis is pretty much the same as it is for a common emitter amplifier. The first thing that we do is that we draw the AC equivalent circuit. And we do that by shorting out the DC supply. So we take 20 volts and we ground it. We're looking for the AC component. We're looking for the effects of the AC voltages. So you short the DC voltages. And then you transfer the parts over one by one from the schematic to the AC equivalent circuit. So you take a look and, okay, RB2 is between the base and ground, and there it is, same point. RB1 is between the base and also ground, because the 20 volt supply is taken to ground. So that goes there. RE is from the emitter to ground, and there's RL. Now, while I draw that, I leave a box for the transistor, and I kind of work around it and do the other parts. And then when I'm ready, I put my appropriate model in the box. And in this case, it's a T model with a beta of 150 and an R prime E of 0.28. The R prime E comes from the Boltzmann's constant formula, 0.025, 25 millivolts over 89.8 milliamps. This is the DC emitter current. Comes out to about 0.3 ohms. Now that we've got all the values for the AC equivalent circuit, we can figure out Z in and Z out by Thevenizing. So we look into the input here, and we reduce all the impedances that we see looking in this direction down to a single impedance. So when I look in here, basically from the capacitor forward, I see one path, a second path in parallel, and then a third branch here, and then these two resistors would be seen in parallel. In the common collector amplifier, if you are at the input, the load is attached to the input. So you include that in your Thevenizing. On the common emitter, it's out over here and it's broken away from the input by the transistor, because when we Thevenize, current sources become an open. So when we're doing Z in, we include RL. So that means Z in is 3 parallel paths, RB1, RB2, and then this third one here, because this is on the emitter side, we need to multiply it by beta plus 1, and that would be R prime E plus RE and RL in parallel. So this is strictly Ohm's law. This is strictly series and parallel resistors and reducing them down to a single resistor. That comes out to 2,713 ohms. Z in, you stand at this point here, you pretend that you're the load, and you look back into the circuit and see what it is you're attached to. Now this gets a little complicated, because if you look back this way, you've got RE to ground, but then you can also go this way through R prime E all the way back through these three resistors. Now in DC, you may have learned a technique for reducing circuits to a single resistance, where you start at the back end, let's say over here, and you work back to the beginning. So let's do that. So if I'm looking this way and I look at the source, I see the source resistance, which is 50 ohms. Then I take into parallel with that 4.7K. Then I bring into parallel with those two 22K. Then as I come over from the base side to the emitter side, I divide these three parallel resistances by beta plus 1. And then I come back a little bit further and I add on R prime E. And then I come back a little bit further and I can see that this path is in parallel with this path. So I put all of that stuff in parallel with this. That is Z out. So again, 1, 2, 3 in parallel, 1, 2, 3 in parallel. You cross the beta line, you divide it by beta plus 1. You come a little further back, you add on R prime E, and then you come and look at it from here and you put all of this stuff in parallel with RE. That gives you a Z out of 0.6 ohms. The final value we need to get out of this equivalent circuit is AV, and we do that by writing V out over V in. We want to solve for AV as V out over V in. And again, the process for this is to identify the nodes or the pieces of wire that are V out and V in. Now V out is over here now, which is across the load, and V in is still this piece of wire along here. Once you've identified those two nodes, you write equations for V out and V in using transistor currents and impedances. So I would look at this and I would say, okay, so V out, if the current's coming out of the emitter and going this way, I would say that V out is IERE. I'm not including the load because we like to find the AV open load, so we detach the load. So I would say that V out is IERE, and I've written that down on top of the equation. V in, when I look at this node here, I could say that V in is the emitter current times these two in series. So IE travels right down, IE travels right down this path here. There's IE. V in is IE times the two of them, and V out is IE times one of them. So V out is IE times RE. V in is IE times R prime E plus RE. Next step would be to get everything in terms of IB using substitution. We could do that here, but we don't really have to because we can see that we've got IE over IE already. So we could cancel them out. So cancel, cancel. That just leaves us with RE over R prime E plus RE. You enter those values. That's 100 ohms over 100.3 ohms. I got 0.6 there, but that should be 0.3. You divide that out, you end up with a voltage gain of 0.998, which is approximately 1. So there's the values for a common collect amplifier. Got a Z in that's not too bad, 2713 ohms. There's a Z out that's very low, but an AV that kind of sucks. 0.998, that just doesn't seem very useful at first. But in fact it is, and I'm going to show you how that's useful with this little demo over here. Let's say I've got a CEAMP. I put a voltage into a CEAMP and it multiplies it by 10, and then it delivers it to an 8 ohm load through a 1 k ohm resistor. Well, this voltage divider here, if I have 1K and 8, well then it's going to be basically the voltage here is going to be 10 times 8 over 1008, which comes out to about 0.01 gain. So much, much less than what you put in. So even though it's got a gain of 10, this is so high that you get almost nothing out. If we attach a common collector amp after that, now this is 1K and 2700. So this is about 2/3 of 10. This is about 6 times bigger here. If I multiply that by 1, I would get the 6 times bigger here, and I would deliver that to the load through 0.3 ohms. Actually, no, 0.6 ohms. 0.6 is correct. So that would deliver that to the load through 0.6 ohms. And 8 ohms over 8.6 is a much better number than 0.01. The net gain of this would be about 6. So the purpose of a CCAMP is if you put it after a CEAMP, you use the CEAMP to get your voltage gain and use the CCAMP to reduce your Z out so that you can drive the load much better. And you use it essentially to match the impedances between Z out and the load better to get a better output.